Okay, I think we can't hear.
The typical problem of being muted. Very much.
We can
Very good. Okay, here we go.
Okay.
Sorry for the hiccup. Yeah. Thanks for having me. Thanks for the nice introduction. So I will talk about discovering equations using machine learning. We heard this in this workshop already a lot. Let me just still sort of frame it a little bit. The idea what we typically do in science to do understanding, right? We have some kind of experiments which we do, and then we observe something, we measure something. Nowadays we can measure a lot of stuff, so that's becoming very prevalent. And then we want to do some theory, and so far we typically do the theory by hand, essentially. And ideally, the theory gives us some predictions. We test these predictions, something explodes or not, or so. Then we try another experiment and we go in this loop, right? And the machine learning perspective sort of on this, and the theory is something that we can understand, right? And that involves typically mechanisms and how things are interacting and so on. So that's really nice. Now, let's say in recent years, we have seen this success of machine learning that has a different perspective, namely that you sort of throw in data, you have some kind of black box model, and it makes some predictions. And the goal is to make as good predictions as possible, but you don't really care what's inside of this box. And when we now want to approach this problem of, let's say, scientific problems, we have some data and we really want to not just do predictions, but also understand something, then we would like to have some kind of white box model. Namely, for instance, that this model is some set of equations that we can introspect and look at. So this is typically also called symbolic regression. And Kevin was also just talking about these parts of his dream code architecture can also solve this problem. And we will solve it here now in a different way. So the idea is we want to identify underlying equations from observed data, right? And so far, typically these problems are solved by some kind of search method, for instance, a genetic algorithm or this neurally guided search. But we will see later a couple of other things what people have done. And so that it used to work only on small scale problems. I mean, progress has been made. Let's see how we can do that with the more machine learning toolbox directly. And my initial motivation was actually to efficiently control a robot, not so much in design. So that's maybe also some design choices are a bit different than maybe in other domains. So, okay, so to get a little bit of an idea why this is so important to have such a good compact model is not just because we want to understand something, but also because we want to make predictions in slightly different situations in a good generalizing manner. And here I have two examples where I see this particularly important. So one case is sort of more to the core of my heart is this model-based control. So let's say I have a robotic system. It wants to plan what it wants to do next. And though it needs to sort of simulate what kind of consequences the actions have. And clearly it wants to plan something it didn't exactly do already because it's kind of boring. You want to do something new. And for that new thing, you need to have a model that predicts this well. And if you have just a black box model that predicts whatever in a new situation, that might be not as good as the models that are grounded on physics or are based on very compact equations. So you need this for data efficiency and safety in the robot control. And clearly in natural sciences, we really want to have understanding, find interpretable models, and we also want a way to put in our prior knowledge. Okay, so just to give you an idea that once I have very good models, I can be very efficient, for instance, in search for planning. So this idea here that I randomly sample trajectories and try to find a good trajectory that does the job. Here I have a little bit of an example of a robot that should, this arm here, this hand with a 20 degrees of freedom hand here should open that door, and it only gets the robot if it opened the door, otherwise not. And here I show you if I have a very good model and I can do planning with some recent advances, you can do this very fast. You only need like about 50 samples per time step to plan a good trajectory. If you give it a bit more, then it does it even better. But I'm just saying, so if you have a good model, that's key to do cool things, cool tasks out of the box. So that system could do any kind of task now. It's not trained for this task. It just computes what could be done. Okay, so let's move on. We go into this framework now, into this setting where we really just get the data, right? Data, pairs of input and output, X and Y. And we take the assumption that the data comes from this functional relationship. So I have a function F, which I want to learn. I want to figure out, this is sort of my equation. And that transforms that into an output Y, and I probably have some corruption, some noise, measurement noise. And ideally, I assume that my data comes from some of the system that I can describe with my function F. You will see in a moment what function class that is. Okay, so as an example, for instance, maybe we get a double pendulum, we observe how it moves, and then from this movement, we want to infer the differential equations. So in this case, f of x would be x dot, so the change, but really for us, it doesn't matter whether this is a differential equation or any other thing. We really only care about this relationship, y equals f of x. And the way we do it, well, we really, let's say, we do this in a very simple way. We take a classical neural network that takes inputs, which are transformed by matrix operations, and then typically you would have a nonlinearity, which would be some kind of sigmoid or other type of a ReLU function. And we replace these by the functions that we really want in our expressions. For instance, a sine function, identity, so do nothing, multiplication, later we will also have square root and logarithm and so on, and maybe also division. And then we go on in this network, so we can take these outputs that we have here, and they can be combined and passed to the next layer and so on until at some point we get our output. Okay, so this thing is sort of our model class. Whatever I can sort of be are able to represent with this, I'm sort of happy. And here you only see one unit of a kind, but of course we would have many. So this would be whatever, 20 cosines, 20 multiplications. So this thing as such represents a gigantic formula, something you will really never want to inspect. So, and then you will see what we will do in a moment. So what we do in regression, right? We want to find the function that fits the data well. So that's our error function, our loss function. So f of x was our function. Now w's are all the parameters here, and y is our target output. And we simply want to minimize that for all the data. And how do we do this? Normally we do gradient descent. So we take this function and go down the hill to find a place where we are fitting well our data. Depending on where we start, we will end up in a certain kind of minimum. That's how these algorithms work. And then the second part is this regularizer here. So this penalty term that penalizes the amount or the size of the weights that I have. And I will explain this in a moment. But the gist of it is that after I do all this learning, I end up not with this glibberish formula, but I end up with very, very few connections that really represent something meaningful. So x1 goes here into identity and then is used in a sign and in a multiplication, for instance, and so on. So I can, if you imagine that all the other connections are gone, then suddenly this really represents a formula that I can actually look at and can interpret, and might also be very good to explain the data because I'm minimizing that loss function. So let me explain a bit why this regularizer here should actually lead to something sparse. And so for that, we start with a little bit of a pictorial illustration here. So imagine these two lines here are my two parameters, only two. I have hundreds, but it doesn't matter. And here, the orange line is the optimal parameters for the data. I can choose several of them, or this line would be fine. And now I sort of have these isolines here. This would be how far I am away from the optimal data distribution. So this is my normal fitting loss. This is an L2 loss on the fit. And here I show the isolines of the L2 loss. So how big are my weights? And clearly I would meet somewhere, right? I would just look in the intersection. And here I would have this solution. So this solution would clearly not sparse. Both W1 and W2 are non-zero. Now the L1 loss. So this L1 loss is the loss that takes the absolute value. So this has isolines which are this funny rectangular shape here. And now if you now look at the intersection of these objects, it's very likely that you end up in one of the coordinate axes. And so this means in this case, W1 is 0 and only W2 is there. But you also see one problem. Actually, you wanted that you had something directly on the data. You didn't want to compromise clearly any kind of fitting performance. So that is namely something that you would capture by a thing that's called L0 loss. I will explain this also in a moment. That would only count how many units are on. And we can, in this first paper, we sort of made a trick to first do this step. And then we just fix all the weights, which are anyway 0, and let them relax to their perfect value. So this is how we did it in our first paper, and that works pretty well. And so a little bit pictorially again, so imagine your parameters at the beginning, they will just sort of try to fit the data. At some point you say, okay, now please become sparse. So a couple of them go to 0, but the correct parameters are not really at their perfect values. And then you relax them and the penalty, and you will find exactly the parameters that you want. You find your constants perfectly. Okay, and then, but this was kind of a bit not super satisfying, let's say, this kind of tricks. And then recently there appeared a method that tries to do the right thing immediately. So you want to minimize the L0 norm. So this is a norm that essentially just counts how many of these weights here are non-zero. Well, we do want to do this gradient descent, but just like this, you can't do it because this is not differentiable. Either you have 1 or 0, right? You count that doesn't really work per se. But then there was this paper that explains how you can do this. They did a trick. I mean, there are several tricks you can do, but this trick worked pretty well. So you, instead of learning, just trying to do this regularizer, you learn a probability of using each of these connections here. And you adapt this probability, and this you can now do in a differentiable manner. And so in this way, you can still do gradient descent, directly learn, optimize it, and you don't have this problem of this not ideally fit constants. So that's pretty cool that we also have implemented, and that works. Good. So now I told you how this all works, but let's see some examples. So let's say I look at an equation where I have a couple of inputs, x1 to x4, so 4-dimensional space. They are somehow here connected by this function. So I have a sign, I have some constants pi, I have some multiplication and some noise. And now I'm giving the system data in a small area of my space. So from -1 to 1, this is the shaded area here. And then I afterwards ask it whatever system I do to give it predictions. And what you see here, this is a baseline. It's just a normal neural network that would perfectly fit clearly the data on the training set, right? I mean, that always works. But then as soon as I go out, really clearly the network can't really do much. But if I'm running this equation learner, how we call this on it, then it can, from this part, it can perfectly identify the exact equation and it's then perfectly everywhere. Just to give you an idea, this space is actually 4-dimensional. So the area that you extrapolate is really big. It's 16 times larger than the place you have seen. And I mean, this is fairly simple equation. You can actually look at the network. You will exactly find the right representation, and you can write down the equation, and you see that it fits pretty well. The constants, everything is fine. Okay, so that was good. Here I have another example, maybe a little bit more tricky one because I have division, and this is always not easy to train. And we have some tricks to do this in the paper. And here is a little bit more baselines. So all these different colors. One thing that I want to draw your attention to is the yellow line is also our system, but without the division unit, so it can't do division. So it would learn something that looks pretty good, but since it doesn't have the capacity to model a division, it would not be able to do it. And then you see it would not extrapolate too well. And the other interesting baseline is this Eureka. This is a very good genetic algorithm search method, so that would search in space. And I thought this would sort of do it, but still giving it a very long time to search it, it would somehow not find the right equation in this case. But often it does. Okay, so now I just showed you sort of already the results, but you might wonder, what kind of, how do I crank this regularization? How do I tune it that I get a good model, right? So we heard a couple of times already through this wonderful workshop today, this week, that Occam's razor is an important concept. Namely, you want to find the most simple formula that fits, or the most simple formula is probably the right one, right? But if it's too simple, then it's wrong. And so this means we really want to find a simple and good performing model. And so you have to look at it on this kind of in the space of performance and sparsity or complexity. So here on this plot, I've shown for every dot is sort of one solution with a particular regularization strength. And then I plot here the dot, means I have here, let's say 9 units, and I have this performance. And you see, if I decrease the number of units by cranking up the regularization, I get very bad models. Clearly they have been too small. And then I have some very good ones. And then if I go up here, they get a little bit worse maybe, but they might be equally well on the training data. But here the color code shows you how well they do if I ask them to predict something that is really far outside. And this is really the thing that tells you whether you got the right equation or not, in a way. And you see here all the interesting models are here. And this is really different from standard machine learning. Standard machine learning would essentially mostly care about the performance on some validation set, but here we are searching through that space of equations, and then afterwards we take the sparsity into account. And this is really then the source of this interpretability, right? Because only if I have this very few equation terms, I can actually do something and look at it. Good. So now let's look at a couple of other interesting examples because they are quite sort of visual. So here, maybe let's look first at these pictures all around. So these are just different equations in 2D visualized, and the black area here is, or within the black circle is the place where we train, and all the other parts we need to extrapolate to. And some of them are really interesting, have very interesting structure. And here you see the performance sort of that you get. The red line here, this red area is the genetic algorithm type. And it's, in some cases it can do it, but mostly it doesn't do it too well. Whereas in this way we do it with this kind of machine learning approach, starting from a big equation and becoming smaller and smaller, we have a good way to find these equations with 4 inputs and quite complicated ones. So here are, sorry, I forgot. Here are some of these equations. So some of them are relatively small, but have some interesting features, and some of them are relatively complicated already. Good. So how about putting some domain knowledge into the system? So this we have been looking at a bit now. So imagine you want to say that, well, I mean, I have some idea that probably it's a system where I have oscillations, so I probably expect some cosine or like trigonometric functions more than polynomials, or I want to have more divisions than exponential, or some other things that you want to put in. Or we have also some problems clearly in this framework at all with exponential and square root and log, because they're all not really nice. They have all these problems of being not differentiable at certain parts, or just explode. And so we have some ideas how, and in the paper we show a few ideas how to work with them. And the other thing that you also want maybe to say that you're not really happy with this kind of funny combinations of cosine of a cosine or x of an x or something. So this we can also now forbid. And this is what we call informed equation learner. Paper's just on archive at the moment. You can have a look. And so something that we didn't really look for so far would be, for instance, to pre-initialize a network with some prior knowledge. For instance, let's say you have some kind of analytical model for part of your system and you would like to already supply it, and then you learn from there. This may be also very, very interesting route to go down. So let me give you one example here. It doesn't really matter. It's a combustion engine torque prediction. So we get input data from that machine, and we need to predict how much torque will it output. And here we show that when our normal system would be that all the terms are equally important. This is the blue weighting here. Then I get, in all the equations that I find, I get this kind of histogram of what terms occur how often. And now let's say I can say in this kind of, for this motor, I want more, I want to penalize the trigonometric functions a lot, but I want to have it more to use multiplication and squares and so on. And then indeed, if I crank up the cost, so the higher the cost, the less I wanted, it really reduces the number of terms I would find of the penalized one. So in this way, I can influence the type of equations that I find. And so that's good. And then here may be an interesting example of such a Pareto front. So here we have the error, and here we have complexity. And before we had this place where this complexity would go down, and you have a kink to the good models, and then you're done. But in this case, you don't see any of this. It just goes down slowly. And now you can sort of pick randomly, sort of where do you want to find a model. Here, this one has a couple of 100 parameters. So that's really difficult to inspect. Although it's still useful, it's very fast, so that you could implement it on an embedded system or so, but you wouldn't really want to try to understand it. But then you can go in an immediate level and look maybe what this one is doing. Maybe as a side note, if you use this genetic algorithm search, you would find with the same complexity, at least what we found, not the same performing models. So these are sort of the dots that you get here. They're a little bit out of the plot, or these two. And you would never get a big equation. So it would never find such a big equation that is very, very good in terms of the prediction performance. But still, this model with the 32 terms is relatively tough. So you look at it, I mean, you can sort of substitute it a bit. So you can clearly take a look. It's polynomial of degree 7 with some cosine terms and so on. So it might be helpful for the engineers. I don't know. Okay. So this is a little bit of a sort of slightly negative result, but also it shows that some systems are simply not really keen to this. So maybe this combustion engine is simply not described by a simple equation. So then we see this here in this result that you can't really find this. Okay, now a little bit of an application to this model predictive control.
5 minutes left.
Yes, good. So I have a Cart-Pendulum, and I can control this on the x-axis, and I want to, and the ordinary differential equations, it doesn't really matter what these inputs here are, the angles and positions of velocities. It looks already pretty messy, and we can now check whether we can train such a system, and we can see that, well, it sort of looks like it works if you randomly sample data points. But what happens if you really run this on a little simulated robot? So we have such a robot. We can move it left and right. We do some random actions at the beginning because we don't know anything. We collect data. From this data, we learn the differential equations, and then we use these differential equations for planning. This was similar what I showed you at the beginning. So if you think about what you can do with your actions, and you find the best action. So essentially, you simulate the different paths, and you'd only take the one that leads you to the place where you want to be, and the other one you discard. You do one step and you replan. And here I can show you this video. So I don't know whether it runs well over Zoom. So this is essentially the training data. So random movements. It doesn't really bring you up at all. At least with never stabilize there. And then once you do this, you can perfectly stabilize the system after this. So you need 2 random rollouts, you learn the equation, and you're done. So that's pretty exciting. That was clearly not shown before. And And yeah, you can do some statistics and see that even if you give a lot of these random rollouts to a normal neural network, these red dots here, it would never really do it because it never sees this thing balancing early. You can only do this if you slowly accumulate more and more data while trying to do this. Okay, now let's see some interesting things that we are looking at the moment is to see whether we can yield uncertainty estimations from this system. So imagine you train your equation, but you're not getting one equation, you get many, and you don't exactly know which one is the right one before you really get some data outside. This is sort of a theory making. You make a couple of theories and then you need to check which one is good. And then you could also sort of consider this as your uncertainty estimation. And you see that these uncertainties are pretty structured. They look really pretty much like the system is behaving. Whereas, let's say, if you take an uninformed Gaussian process, that wouldn't do that. If the Gaussian process, of course, has the right kind of kernels, then it would also do it. Now, I would like to use the last few minutes to compare a little bit the different methods. So this is maybe a little bit of a full slide here, but I wanted to also compare a little bit against this, the stuff that we have seen the last days, and I hope I'm fair to everybody here. So I start, maybe the first row is this genetic algorithm search for symbolic regression. So I have a couple of columns here. I don't know whether they are super helpful, but let's say whether they are easy to implement. Yeah, they're pretty easy to implement, but if to make it really good, it's also difficult to make them really fast. This outcome is not really different. The system itself is not differentiable. What I mean by this is that I cannot take the system and put it into an architecture where I have, let's say what Nathan was telling about. I have first some feature extractor, then I would try to run the symbolic regression, and then afterwards I do something else. So for this, I need some end-to-end learning. This I can't do with this. And there are some cons that this typically works only for small equations, and constants or floating point constants, pi or something, is difficult. Then we have this AI Feynman, which is sort of a bit more complicated to implement, and it's also not differentiable. It finds very, very good equations. It's really amazing. It gets the main knowledge in terms of physics, so that units match and a lot of stuff that is really specific. And I think it's pretty restricted to sort of the particular physics domain. Then we have also this reinforcement learning based search method, so the deep symbolic regression, which has I didn't even fill all of the rows here, sorry, which is a bit more complicated to implement. It's also not differentiable. It finds pretty good equations, I have to say, and it also has some troubles with the constants, but otherwise it's also a very interesting method. Sorry for not filling out this. Then there is the thing that is also in this workshop, the transformer version, so this neurosymbolic regression that scales, which is a super interesting thing. So that essentially tries to learn how to guess good equations. The dream coder could also be sort of roughly in this line here. It really are these methods that use data to sort of pre-train the system, and then at a time when it gets some data from the real system, it has a very good guess of what to do, and then you use these things to guide your search. They are difficult to implement, but in a way, I have here this little green thing indicating that they are pretty good once it's trained. You can just use that transformer, and then it's pretty easy. It's very fast and pretty accurate. Then we have this Cindy method, so this sparse linear regression. It's easy to implement. It's also differentiable to some extent. I don't want to go into the details now because I don't have time. And you can't do functional composition. So the library is fixed. And then our method is relatively easy to implement, but it's also not super easy to train it. So that's why I have some yellow bar here, a circle. It's differentiable. So I can just plug that into normal architecture, train end to end. It works maybe as the only system, I would say, also Cindy, with large systems, many degrees of freedom. I don't care how many inputs I have. And we find often maybe too complicated expressions to look at. So this is maybe a little bit of a drawback. Okay, so now my time is pretty much up. We have some interesting applications in physics. It was yesterday on the poster to apply this to density functional theory, and where you exactly use this end-to-end differentiability you want to learn the density function, so the object that describes the density of particles essentially in a fluid. And there are certain bits of this part that you don't really know analytically, and we can try to learn a good equation. So this is an example where you have a physics knowledge of how this entire system should be designed. So with here, differential operators and everything, but parts of it are unknown, and there you plug in this equation learner. You train it on part of the data, and then you ask how well can I predict the system for different densities, for instance, or for different potential functions. And without going into the details, it really works nicely for the simple systems that we looked at. And now we are looking with Alessandro into how this can be done for more interesting fluids. Okay, so that's it. To summarize, so this learning equations from data is really interesting. We get interpretable results, and we have with them, we have great extrapolation capabilities. Our system can be used inside of bigger models. So for instance, in systems where you know already how post-processing or pre-processing should work, or we want to also learn this with a normal standard neural network. And yeah, it's awaiting your discovery, right? So this work is together with my fantastic collaborators, and our code is also on our GitHub page.